This is going to be the beginning of a video series on an aspect of mathematics called abstract algebra or group theory or finite fields, um, all kind of parts of the same thing. But the reason why I'm going to be talking about all of these things is because this branch of mathematics is extremely useful in cryptography and error correction. And so I think that I shall approach it beginning talking about cryptography. In the case of this particular video, I'm going to explore exactly how RSA works. Now, RSA is an interesting algorithm. And it seems very simple, but the reason why it works is actually kind of subtle and interesting. And everybody knows, of course, well, perhaps not everybody, but most people with some familiarity with the RSA algorithm knows that the RSA algorithm involves two prime numbers. I'm going to, for various reasons, pick primes that are of the form of 2 times a prime number plus 1. So in this particular case, 2 times 23 plus 1, and 2 times 29 plus 1. 59, is that a prime number? Let's check whether 59 is a prime number. So let's see if 59%, 2 of course is not 0. And then the last one be 11. Okay, yes, definitely 59 is a prime number. So our first prime is going to be 47, and our second prime is going to be 59. So in RSA, given that we have these two primes, we know that the public key is going to be the two primes multiplied by each other, and then we'll pick some other number, a small number, usually also a prime. So it'll be, in fact, actually the small number almost certainly should be a prime. So we pick p times q and then 5. So p times q is our public value, and 5 is the public exponent. And then we need what the private key is. And of course, we know that p and q are going to be in the private key. But what else needs to be in the private key? There is, in fact, a number that can be derived from p and q that doesn't necessarily have to be in the private key, but usually is put in the private key data simply to avoid having to recompute this number every time. And that number is related to 5, the public exponent. How is this number computed? Well, first we need to look at an algorithm called GCD. GCD, greatest common denominator. So the basic idea of the GCD algorithm is that, and Python of course is not going to consider that valid, but so the greatest common denominator is the largest number that divides both inputs. So GCD takes two different numbers, and then it will tell you, in fact, actually can take n different numbers, but it has to be at least 2. So it takes two different numbers, and then it will tell you whether those two numbers are, in fact, divisible by a common number, and if so, what that common number is. And of course, it will, in the most degenerate case, result in 1, because then that means they don't actually have any common divisors. So let's take an example here, like 15 and 35. So we know that the GCD of 15 and 35 is 5. But it would be really nice to have a way of figuring this out without having to sort of eyeball it and think, or try random factors and find out what the answer is. And so I'm going to show you a way in which this could work. 35%, or percent 15 is 5. 15% 5 is 0. 5 is the greatest common denominator. Let's try this with a couple of other numbers. Like let's try 48 and 39. Right? So 48% 39 is 9. 39% 9 is 3. 9% 3, 0. So the greatest common denominator of 48 and 39 is 3. 48 divided by 3, 39. We'll do integer division here. I'm using Python 3, so yes, integer division is //. So why does this work? So if you think about if numbers have a common factor, that means, say we have numbers a and b. So if they have a common factor, then that means that f times a, 2, equals a. So that there's some number a that's such that f times a2 equals a. And also some number b, or b2, such that f times b2 equals b. That means f n times n times f times a2. No, I'm getting ahead of myself. And so that means that there is some number f such that for f, there's f times a2 equals a, and also f times b2 equals b. That is what it means for a and b to have a common factor. And if that number is 1, of course, then a and b don't have a common factor. But we're looking for the largest f such that this equation holds true. So let's look at what we were doing up above. So we were taking a% b. Well, what we're really looking for here is we're looking for b times x plus r equals a. And so we're looking for what the value of this r is. That is what we were getting with percent. We are trying to find out what r is. So let's try writing b as our common factor thing. F times b2 equals f times a2, like that. So substitution. Then the next step is to subtract r from both sides. R. And then divide both sides by f. Right? And then we'll simplify. And then we'll subtract a2 but from both sides. And then we'll just reverse the sign. Just to make everything all neat and positive. So what we are saying here is that a2 minus b2 times x equals r divided by f. Well, a2 is an integer, b2 is an integer, x is an integer. a2 minus b2 times x must be an integer. that means r divided by f must be an integer. So that means when we find out what r is, we are coming up with a value that is also divisible by f. And we're also guaranteed that that value is going to be smaller than b. If it were larger than b, that would mean we could take away another b from a to a, and then we'd end up with an r that was smaller than b. So r is going to be smaller than b. So that's a way of progressively getting a smaller and smaller approximation for what f is. And then, of course, once we get to what f is, we'll discover that we have a remainder of 0, and we're done. There is, in fact, a way to write this as a Python function. And this is it. I've pre-written this nicely here. So the assertion conditions, of course, is that a and b are greater than 0. And I could have, thrown exceptions when that wasn't true and been much nicer about it, but I just make it an assertion failure, and that's that. And then, of course, if a% b equals 0, then we've found our greatest common denominator, and it's b. Otherwise, we find out what the remainder is, and then we check on the remainder of GCD b and r. And that's the algorithm right there. And we can test it. GCD 1535. GCD 4839. GCD 47 59 1. So that's all well and good. So we have this wonderful GCD algorithm. Why do we care about GCD? Well, it turns out that we can modify this GCD algorithm in kind of a clever way. We can modify this GCD algorithm to tell us not only what the greatest common factor is, but we can also get it to tell us what, if we have n times a minus and m times b equals whatever our greatest common factor is. So we can modify it to actually tell us what n and m are. That largely involves keeping track of how many times b went into a each time. The technical name for this algorithm is called the extended GCD algorithm. And here is a bunch of comments about the extended GCD algorithm that I wrote earlier, as long as an explanation for how it works. It's basically the GCD algorithm all over again. And also I rewrote the GCD algorithm to no longer be recursive. It is instead an iterative algorithm here with the while true section. And I did that because, of course, it exits via return all the time. And so it just continues until it exits via return. And here's an explanation for how it would work for a couple of different numbers. In this case, discovering the GCD of 23 and 15. We start out with two different equations about 1 times 23 minus 0 times 15 is 23, and 1 times 15 minus 0 times 23 is 15. And then we can sort of subtract these equations from each other and end up with smaller and smaller numbers. And along the way, sort of build up what n and m happen to be. So I actually have the definition for extended GCD here sitting in the history of my IPython session. And so we'll just define it here, and we'll test it out. Now, this results in something funny. It results in the extended GCD being 0. That means I actually have the algorithm continue one step farther than it really needed to continue. It should have stopped before it got to 0. But for our purposes, we don't care. The extended GCD algorithm is, in fact, for various reasons, the most useful when there is no greatest common denominator. But let's test out the answer it gave us for 15 and 35. So 7 times 15 minus 3 times 35. Well, we get 0. And that sort of makes sense. Like if we factor out the common, we get 15 divided by 3. We happen to know the greatest common factor is going to be, 5, is 3, and 35 divided by 5 is 7. So if we multiply 15 by 7, we put the 7 into 15. And then if we multiply 35 by 3, we put the 3 into 35. So both sides end up being 7 times 3 times 5, which is 105. And so 7 times 15, 105. 3 times 35, 105. So there we go. But let's try using this for something where we get something slightly more interesting out. Let's try 13 and 35. There, the greatest common denominator happens to be 1. And so 27 times 13 minus 10 times 35. There we go. We get 1. Now, this is really important for a very interesting reason that happens to be related to group theory and Euler's totient function, which I don't expect you to necessarily know what are right now, but we'll get on to how to actually use this extended GCD function in RSA. So we happen to know that we have p times q comma 5 as our public key, and p comma q so far as our private key, but we need something to go along with the 5. And I'll tell you that what we want is extended GCD of p minus 1, strangely enough, and q minus 1. The reasons for this are related to Euler's totient function, and 5. So we get 1601 as our answer. So let's try RSA here. And RSA is really simple. RSA is m to the public exponent, and which in this case is 5, mod pub key, which in this case happens to be, what was it? P times Q. Where did we? Oh, yes, there we go. 2773. So mod 2773. So that means we need to pick a message. And there's one other interesting thing. Like suppose 5 was a much larger exponent. Like, 5 are, like, we'll pick 73, our message, and we'll pretend we're using a much larger exponent, like 4,000. It's a really big number, right? And it's a lot of number to be storing in memory. So it might be really nice to have sort of an optimization for this. And luckily, Python has this really nice function called pow. And pow allows you to compute powers mod something. And in fact, there is a way to compute powers mod something that is far cheaper than computing the power and then finding the modulo as separate operations. So we will be using the pow function. So p times q comma 5, and then the extended GCD. We'll get the numbers back on our screen again. So we'll pick a message. We'll pick 632. Could have been anything. I could have used the random number package in Python to come up with a message. Doesn't really matter. But we want star star 5. So we're going to use actually the pow function here. Pow 632 5 comma p times q. That's our mod. So this 2574 is going to be our message that we're sending. Now, somebody who sees 2574 really has no way of figuring out that the original message, even though they know that the public exponent was 5, like, that's actually a slight danger of the RSA algorithm. Say we did 2 comma 5 p times q. Well, there we've got a problem. Like 32 is obviously has a fifth root, and that fifth root is 2. And so we know that the message that was being sent was 2. So it turns out to be pretty useless here. But if we do import math do math.log 2574 divided by math.log 5, which is the way to find the logarithm base 5, 2000. Well, it's not an integer, right? There is no integer to the power of 5 that gives us 2574. So we're left with trying to solve a problem called the discrete logarithm problem, which in fact turns out to be pretty hard to solve. So we can't really find out what we took to the power of 5 to get 2574. That's a hard problem. And so if somebody only knows 2574, they're not going to be able to turn it into 632 unless they happen to know 1601. And I'll show you. POW 2574, 1601, comma, P times Q. Well, what do you know? 632. How on earth did that work? Well, you'll have to tune in for the next video to find out.